Picture this. It is the late 1800s, and you are standing in the middle of Manti, Utah.
Right.
It's this quiet, remote farming community, nestled right at the base of the towering Wasatch Plateau.
Beautiful area.
Yeah, exactly. You've built your home here, you've planted your crops, you've established your whole life in this valley. And then one afternoon, you hear it, this low, terrifying rumble echoing down from the steep canyons right above you.
Oh.
But it's summer. So, it's not an avalanche of snow.
Right.
What comes pouring out of the mouth of that canyon is a massive, just violent wall of mud, rocks, uprooted trees, and debris.
Just terrifying.
Totally. It tears down the mountain, completely ignores the banks of the creek, and just violently buries the streets, the fields, and the homes of your town.
Wow.
And here is the truly terrifying part of this historical reality. It doesn't just happen once.
Yeah, that's the crazy part.
Right. Between 1888 and 1910, this specific community is repeatedly battered, repeatedly buried by these catastrophic mud flows.
It really shatters our modern, I guess, somewhat sanitized view of early Western settlement, doesn't it?
Oh, absolutely.
We tend to imagine this pristine, untouched wilderness being gently cultivated, But the reality for places like Manti and dozens of towns like it across the Intermountain West was one of just acute, terrifying environmental crisis.
The land was literally collapsing on top of them.
Literally. Yeah.
And that collapsing land is exactly the mystery we are unpacking today.
I'm excited for this one.
Me too. We have a massive stack of historical dossiers, early U.S. Forest Service research files, and state history materials in front of us.
Lots to go through.
Yeah, and we are going to use them for a specific mission. Today, we are stepping into the shoes of an introductory ecology student to explore the birth of a brand new scientific discipline.
Rangeland Ecology.
Exactly. We are looking at how a series of catastrophic floods in a Utah farming town forced the federal government's hand, leading a young scientist named Arthur Sampson to invent the science of grass, soil, water, and livestock.
It's such an incredible story.
It really is. And just as importantly, we are going to look at why this seemingly pure, objective environmental science immediately sparked a political wildfire. Oh, a huge one. One that burns to this very day.
To really understand the stakes of this deep dive, we have to adjust our modern understanding of the institutions involved.
Right, because when we hear U.S. Forest Service, our brains immediately go to, trees.
Exactly. We think of managing timber harvests, preventing massive forest fires, that sort of thing.
Smokey Bear.
Right, Smokey Bear. But what gets completely lost in the popular imagination is that half of their foundational mandate is actually range.
Wait, really, half?
Yes, half. The name on the door of their regional research divisions isn't just forest research. It is literally Forest and Range Experiment Stations.
Huh. I don't think I ever knew that.
Yeah, and they had to earn that title. It wasn't just handed to them. They earned the word range through decades of grueling trial, error, and incredibly meticulous observation.
Out in some of the most unforgiving environments on the planet.
Exactly. The deserts of Arizona, the mountains of Utah.
But before we get to the science that eventually stepped in to save these landscapes, we have to look at the math.
The math is staggering.
It is. We have to understand the sheer scale of the destruction that forced the government to act. Because we aren't just talking about, a few too many cows in a meadow.
No, not at all.
We are talking about the catastrophe of the unclaimed commons.
That is the precise term for it. In the late 19th century, following the Civil War and the expansion of the railroads, we're looking at millions upon millions of acres of public domain.
Just wide open land.
Right. This was land that belonged to the federal government, which essentially meant it belonged to everyone.
And therefore managed by no one.
Exactly. And on this vast expanse of land, there was forage, native grasses, shrubs, forbs, and crucially, it was entirely free.
Free grass. Yeah. So if you had the capital to buy the animals, you could just put them out on the public domain to eat?
Yep.
And it didn't cost you a single cent in rent or grazing fees?
Not a penny. It was an economic incentive structure that practically guaranteed disaster.
I like to think of it like throwing a massive house party.
Okay, I like this.
Right. So imagine you throw a massive house party and you tell everyone they can invite 10 friends.
Uh-oh.
Right? But nobody brings any food.
Oh, no.
Exactly. Eventually, the house is completely trashed and everyone starves.
That is exactly what happened. If I put 100 cows out there, I make a profit. If my neighbor puts 500 out there, he makes 5 times the profit.
Because the grass is free.
Right. The only limit to your wealth is how many animals you can physically acquire and just dump onto the landscape.
And that fueled explosive growth, unchecked growth. Let's look at the historical estimates from the USDA because they paint a terrifying picture.
Go for it.
In just 17 Western states, the cattle population skyrocketed from roughly 8 million animals in 1870 to more than 21 million by 1886.
It's just wild.
8 million to 21 million in just 16 years. That is nearly a tripling of massive herbivores on the exact same finite amount of land.
And that doesn't even account for the millions of sheep that were also being introduced at the exact same time.
Right. So let's break down the actual physical mechanics of what that many animals do to an arid ecosystem.
Yes, because people really underestimate the violence of overgrazing.
It's not just that the grass gets short.
No, not at all. When you have millions of hooves trampling the soil and millions of mouths pulling up native grasses, you fundamentally alter the hydrology of the land.
The water cycle.
Right. The native grasses of the American West, like blue bunch wheatgrass or grama grasses, they evolved with grazing pressure from bison.
Sure, bison were everywhere.
But bison moved constantly. They would graze an area intensely and then not return for years. What the livestock boom introduced was continuous, unrelenting pressure year after year.
Because there were no fences.
No fences, no rotation. The cattle and sheep would eat the most palatable, nutritious grasses right down to the dirt.
Oh, wow.
And because they were never removed from the pasture, the moment that plant tried to push up a new green shoot using its root reserves, the animal would just bite it off again.
And if you do that enough times, the root system starves. The plant gives up and dies.
Yes. And when the root systems die, the physical architecture of the soil just completely fails.
Because the roots are like the rebar holding the concrete together.
Exactly. Those dense mats of roots are the only thing holding the topsoil in place against the wind and the rain. When you remove them, the land simply loses its structural integrity.
And then you add the weight of the animals.
Right. You have the mechanical action of the hooves. Millions of heavy animals compact the exposed dirt, pressing out all the microscopic air pockets.
Turning the surface of the earth into, like, a hardened crust.
A literal crust. So when the rain eventually falls, it can't soak into the ground. It hits that compacted crust and immediately sheets off.
And as it runs downhill, it gathers speed, taking the loose, rootless topsoil with it.
Exactly. You get severe gullying, where the water carves deep, jagged trenches into the earth. The landscape is literally bleeding dirt.
And nature has a very brutal way of correcting an imbalance like that.
It really does. The land was stripped bare, meaning those 21 million cattle had very little to eat to build up their fat reserves for the winter.
They were weak.
Incredibly weak.
Yeah.
And then the natural climate cycle of the West swung hard. The brutal, historic winters of 1885 and 1886 hit.
The Great Die-Up.
Precisely. It was a slow-motion disaster that culminated in an acute catastrophe. The weakened, starving herds just couldn't survive the deep snows and the freezing temperatures.
They died en masse.
Millions of carcasses littered the draws across the West. It bankrupted syndicates overnight and served as this horrific reality check. The open range had collapsed.
Okay, so it's a tragic story, but here's where we have to look at the institutional response. Why did this become a federal problem?
That's the key question.
Right, because starving cattle and bankrupt ranchers are terrible, but why does the federal government decide it has to step in and manage the actual dirt?
Because the consequences of the collapsed range didn't stay on the range.
Ah.
The visible result of all this overgrazing was erosion and flooding on a scale that was directly menacing downstream towns.
Like Manti.
Like Manti. When the high mountain watersheds are stripped bare and compacted, the spring snowmelt doesn't slowly percolate into the groundwater. It flashes off all at once.
It became a federal issue because the failure of the upland range was physically destroying the lowland settlement.
Exactly.
Okay, so the problem is undeniable. The mud is literally in the living rooms. The government knows it has to act.
Right.
In 1897, Congress passes the Organic Act. This authorizes the creation of the forest reserves and gives the agency authority to regulate grazing.
Provided it didn't injure forest growth.
Right. So by 1906 and 1907, the newly minted U.S. Forest Service is actively trying to build out a regulatory system. They want to issue grazing permits, set limits on herd sizes, and charge fees. But wait, at this point, how did anyone even know how to fix it? Like, did they have any actual rules or math to base this on?
That is the exact question every angry rancher was asking the local forest ranger.
Right. If I am a rancher who has run 1,000 head of cattle on a mountain for 20 years, And some 25-year-old forest ranger rides up and says, actually, you can only run 400 cattle here, and you owe me money. I am going to demand to know how he got that number.
And the reality was, initially, they essentially had to guess.
Wow. Just a guess.
Pretty much.
Yeah.
And that exposed a massive, glaring blind spot in the federal government's plan. They had the legal authority to regulate the public lands, but they had absolutely zero scientific data to back up their numbers. No one actually knew how many animals the land could handle.
Because the science of rangeland ecology literally didn't exist yet.
It didn't. Botany existed. Forestry existed. But the complex interaction between specific soil types, weather patterns, plant species, and large herbivore digestion, nobody had studied that.
That's wild. So they had to establish a baseline concept, the carrying capacity.
Yes, carrying capacity is the fulcrum on which all of this history balances.
Let's define that clearly.
Carrying capacity is the maximum number of individual animals that a specific environment can sustainably support over a defined period of time without destroying the long-term health of the vegetation or the soil.
It sounds like a simple definition.
It sounds simple, but calculating it in the real world across millions of acres of highly variable terrain is incredibly complex.
So, to figure out how many animals the land could survive, the Forest Service had to build the world's first outdoor laboratories.
Right.
And they didn't start in some lush, forgiving alpine meadow. They started in the hardest, slowest healing environment possible, the desert.
It was a very strategic choice.
Yeah.
In 1903, they set aside a massive tract of land in the foothills of the Santa Rita Mountains, south of Tucson, Arizona.
The Santa Rita Experimental Range. We are talking about roughly 66,000 acres of Sonoran desert grassland.
I want to pause on that number. 66,000 acres. That is over 100 square miles of desert.
That is not a laboratory with beakers. That is a landscape-scale research facility.
It had to be. You can't understand how a herd of cattle utilizes a desert by fencing off one single acre. You have to observe how they move across elevations, how they seek out water sources.
The Santa Rita is incredibly significant.
It is one of the oldest experimental ranges in the entire world and the oldest continuous research area ever maintained by the USDA Forest Service.
So if I'm one of those early researchers arriving at Santa Rita in 1903, what exactly am I looking for? What are the mechanics of the experiment?
They had to start with the absolute fundamentals. Before you can determine carrying capacity, you have to know what you actually have. So the first questions were taxonomic and phenological.
Phenology, that's the study of cyclic and seasonal natural phenomena, right? Like in relation to climate and plant life.
Exactly.
Mm-hmm.
What specific forage plants naturally grow here? When do they green up? When do they flower? When do they drop their seeds?
Because if you don't know the life cycle of the grass, you don't know when it is most vulnerable to being eaten.
Precisely. And they were also asking incredibly urgent restoration questions, like if a section of this desert has been grazed down to bare dirt, can it come back? And how long does it take?
Healing a desert is a completely different game than healing a pasture in, say, Ohio.
Oh, totally different.
If you plow up a field in Ohio and walk away, it will be covered in green weeds in a month. But if you destroy the soil crust in a desert that gets 10 inches of rain a year, it might stay a barren wasteland for centuries.
The ecological margins for error are just razor thin. So to study an environment that changes at a glacial pace, you need a very specific scientific tool.
You need time. You need decades.
The true genius of the researchers at Santa Rita is that they designed experiments intended to outlive them. For over 120 years, scientists have been measuring the exact same plots of land.
That is mind-blowing.
Pounded steel stakes into the ground. Season after season, decade after decade, researchers have returned to those exact same spots.
It's like taking a photograph of the exact same patch of your backyard every single day for a century.
Yes.
You'd see exactly how droughts, rains, and foot traffic change it. You wouldn't be relying on memory. You'd have an undeniable visual and data-driven record.
That unbroken series of data, it's an invaluable scientific treasure. Even after the Forest Service handed Santa Rita to the University of Arizona around 1988, this incredible data record continued.
And they replicated this, right, with the Narrated Experimental Range in New Mexico in 1912.
By executive order, yes. Together, Santa Rita and Jornada anchored the science of arid rangelands.
But while the researchers in the desert were patiently collecting data drop by drop, waiting for the desert to reveal its secrets, The situation up north was entirely different.
The mountains didn't have time.
Exactly. The crisis in the high country was acute, violent, and actively destroying towns. Which brings us directly back to our opening hook, Manti, Utah.
Right.
While Santa Rita was mapping out desert phenology, Manti was actively digging mud out of its living rooms.
Let's look closely at the geography here.
The Wasatch Plateau is a high-elevation mountain range. It catches a lot of snow, it has steep gradients, and the soils are naturally highly erosive if they aren't held in place by vegetation.
And for decades, massive herds of sheep and cattle had been driven up into those mountains every summer.
Right. And the townsfolk down in the valley were looking up at those mountains and connecting the dots. They pointed their fingers straight at the unregulated grazing and said, "You are causing this."
Mm-hmm.
Now, here's an analytical question. Were the townsfolk just looking for a scapegoat, or were they actually right?
They were entirely correct. This wasn't a scapegoat situation. The mountain watersheds had been grazed so incredibly hard that the entire hydrological function of the mountain had been broken.
Let's explain the mechanics of that. How does eating grass on a ridge lead to a boulder crashing through a house in the valley?
It comes down to infiltration versus runoff. In a healthy alpine watershed, you have a dense layer of grasses, and below that, a thick layer of decomposing organic matter.
A litter layer.
Right. When rain falls, that vegetation acts like a giant sponge. It slows the water down and gives it time to slowly infiltrate the porous soil. It provides a steady, safe supply of water to the valley all summer.
But when you introduce thousands of sheep and cattle, they eat the sponge.
They eat the sponge, and they trample the soil. The rain hits bare dirt. The physical impact of the raindrop itself shatters the soil structure. Add in the soil compaction from the hooves, and the infiltration rate drops to near zero.
So the water doesn't soak in. It immediately runs overland, picking up velocity and massive amounts of sediment. By the time it reaches the mouth of the canyon, it is a devastating wall of mud.
Exactly. And the political pressure generated by these flooded towns was immense. You can't ignore a town that is holding a shovel while petitioning Washington, D.C.
The Forest Service had to act, and they couldn't just send a ranger with a notebook.
No, in 1911, they selected a site in Ephraim Canyon for a range and watershed research station. It was later named the Great Basin Experiment Station.
And the mandate of this station was a massive paradigm shift.
It was. Its founding charge wasn't just how to graze, but specifically how rangeland vegetation governs erosion and floods. For the first time, grazing was inextricably linked directly to watershed health.
The idea that the grass on the highest ridge decides if the town in the valley survives the spring runoff?
Yes, but they needed someone to actually invent the solutions. Enter Arthur W. Sampson in 1912.
Ah, here we go.
He was a young scientist handed the keys to a wrecked canyon. Over the next decade, he practically invents a field from scratch. He becomes the first person in America referred to as a range ecologist.
So if you are an introductory ecology student listening to us right now, take notes because Sampson is about to build your entire curriculum.
You really did.
Let's break down Sampson's toolkit. Breakthrough number 1, carrying capacity made usable. How did he turn guesswork into a measurable metric?
By balancing supply and demand. He and his team went out into the field and physically measured the supply of forage. They established sample plots, and they systematically clipped the vegetation, dried it, and weighed it.
They are literally out there with shears, cutting grass and putting it on scales.
Exactly. To calculate the exact biomass of forage produced per acre. Then they correlated that with the nutritional needs of the livestock.
Which led to the Animal Unit Month, or AUM, right? The amount of forage required by one cow and her calf for 1 month.
By creating the AUM, he created a standardized currency. A ranger could look at an allotment and mathematically defend charging a fee or setting a limit.
Brilliant. Okay, breakthrough number 2. Deferred and rotational grazing. What was his solution to continuous grazing?
Well, continuous grazing ignored the biology of the plant. Cows eat the tastiest grasses first, right down to the dirt, and they keep doing it every time the plant tries to grow.
Until the plant starves.
Right. Sampson realized the plants needed a break to complete their biological cycle. His solution was to defer grazing on a specific pasture until the key forage plants had a chance to reach maturity and set their seeds.
You wait until the plant has finished its job for the year.
Yes. You keep the herd somewhere else during the spring. Then, in the late summer or fall, after the seeds have dropped, you bring the animals in. And the brilliant part is, the animals become a restorative tool.
Oh, because their heavy hooves trample the freshly dropped seeds directly into the dirt? basically planting the next generation of grass.
Exactly. They act as biological planters. Then you rotate the herd out. By carefully timing the livestock movement, you allow the damaged landscape to recover naturally over time.
Working with nature instead of against it. Okay, breakthrough number 3. Reading the land from its plants, using indicator species. I love this one.
That's so clever.
It's like a medical analogy. Just like a doctor looks at your vital signs, your temperature, your blood pressure, to diagnose an illness, Sampson taught managers to look at the plants to diagnose the land.
He adapted the theory of plant succession. Succession is the predictable way a plant community rebuilds itself after a disturbance. From fast-growing pioneer weeds to a complex, stable climax community of deep-rooted native grasses.
And he identified specific indicator species for each stage.
Right. He categorized the range into 4 successional stages: excellent, good, fair, and poor.
So a ranger could just ride out, look at the species currently dominating the soil, and instantly know if the ecosystem is collapsing or recovering. The plants act as a living dashboard.
Precisely. Empowering field staff to make localized scientific decisions.
But sometimes the land is too far gone for natural succession. Which brings us to breakthrough number 4, revegetation and the 90-year photo plots.
Sampson pioneered early methods for artificial seeding, but the most compelling legacy is how he recorded it. In 1913, Sampson and colleagues like Lincoln Ellison started the permanent photographic plots.
They drove heavy steel stakes into the ground, took a picture, and then returned to those exact same stakes to re-photograph that specific patch of land for 90 years.
Up until 2003. You can literally watch a barren gully slowly soften, fill with weeds, transition to grasses, and become a stable hillside. It provided an undeniable visual record of vegetation change.
You cannot argue with a 90-year time-lapse.
No, you can't.
And Sampson's methods didn't just stay in a Utah canyon. He earned his doctorate in 1917 while directing the station, and then in 1922, he left for a professorship at the University of California, Berkeley.
That move to Berkeley is huge. In 1923, he publishes a book called Range and Pasture Management. It was the very first comprehensive college textbook on the subject.
So he went from being the first range scientist to the field's first teacher.
He heavily influenced generations of future scientists. That's why he's the father of range management.
And the agency transformed, too. Experimental stations formalized range management as a distinct federal discipline. They weren't just handling it on the side anymore.
Right. Through the late 1920s and 1930s, regional stations literally changed their names, like the Southwestern Forest and Range Experiment Station in 1930, cementing that dual mandate.
Okay, so the science was proven, but science happens in a canyon. Application happens in the real world, and the real world is highly political.
It is intensely political.
Establishing a carrying capacity is ultimately establishing a limit. And a limit on public land is a direct limit on a private citizen's livelihood.
Exactly.
We have to impartially map the two sides of this deeply entrenched conflict. Let's look at the conservationist view first.
The Forest Service saw this as the necessary, overdue stewardship of a rapidly collapsing commons. Fees, herd caps, and seasons were required to save the land from total ruin.
Triage to save a dying patient.
Right. But the local user view was entirely different. To the ranchers and miners who had grazed the public domain for free for generations, this felt like a distant federal government suddenly fencing off land they considered theirs.
Using scientists with notebooks to justify dictating their local livelihoods?
That's exactly how it felt. The science didn't exist in a vacuum above the fray. It was the instrument of the politics. Every grazing permit was a scientific finding that came with a price tag and a boundary attached.
And this tension culminated in the 1934 Taylor Grazing Act. What did that legislation do?
It extended federal control to the remaining 80 million acres of open public lands. It entirely ended the era of free access. It tied grazing privileges directly to the ownership of adjacent private-based property.
So if you were a nomadic sheep herder without a big private ranch, you were locked out.
Exactly. It solved many ecological problems, but it codified the political resentment.
That distant federal authority overriding local claims, that grievance never went away. It foreshadows future clashes we see in other sources, like the Sagebrush Rebellion in the 70s or the Idaho County Posse Comitatus.
It's the exact same fundamental argument happening decades later.
So to summarize our journey, we saw how the devastation of the open range led to the creation of Santa Rita and the Great Basin Station, how Arthur Sampson read the plants, invented rotational grazing, and gave the Forest Service the tools to heal the land.
All while inadvertently sparking a century-long debate over federal versus local control.
Which gives us a great takeaway. The next time you see a fenced-in pasture on public lands or read about a debate over management, remember that those dividing lines aren't just political. They were drawn over 100 years ago by ecologists trying to stop a mudslide.
It's incredible to think about. Every fence line carries the weight of that history.
It really does. And I want to leave you with a final lingering thought to ponder. We just talked about 120-year unbroken data sets and 90-year photographic records showing undeniable ecological truth. In our modern era of information overload, instant gratification, and constant political disputes over the environment, if we started a 100-year ecological photo plot today, would society actually have the patience to wait for the results? Or would we just spend the next century arguing over the camera angle?